There was a lot of question at the intermission about sparsity, and apparently Jeff Hinton and probably Joshua explained how much sparsity is important, and here am I to explain why sparsity is useless. So who's right? And on one hand, you have the father founders, and then there's this guy coming. So I'm going to explain why at the end sparsity is useful, but why it's very tricky. It's very tricky because behind the word sparsity, there are very different notions. I explained there's the notion of analysis, synthesis, which are two very different things. Basically, what I'll explain tomorrow is that sparsity is very important at the learning stage. At the recognition stage, you have to use it in a stable way. And that's what people are doing in these networks. But it doesn't appear very often within these explanations. So I will come back to that question about sparsity. OK, let me continue. Now I would like to continue by showing why what I've been describing ends up being a deep neural network. Let's look at what's happening. So we have a signal, x, and a wavelet transform. But as I explained, I'm not going to keep the phase of the wavelet transform. I'm going to kill it with this modulus, or this yes. And so I have a nonlinear operator u, which associates to x the averaging. Averaging is what is going to build the invariant. And then the modulus of the wavelet transform. Now, the wavelet transform is a linear operator, and a modulus is a contractive operator. What does that mean, a contractive operator? If I take two complex numbers, a and b, okay, if I look at modulus of a minus modulus of b, as you know, this is smaller than the difference between a minus b. So that means the modulus operator that I applied here is bringing things closer together, numbers closer together. It's contracting. And because of that, this operator is going to be contracting. In other words, it's going to bring signals closer together. Wavelet transform is unitary. It preserves the distance. The modulus brings things closer. OK, I have my signal x. Let me apply u. If I apply u, I compute the average of x. This is an invariant, not very informative. And then I get the modulus of the wavelet coefficients. These will be the inside node of my network. Okay? For any wavelet, I get a node which builds a signal. It's a convolution, nonlinearity, the pooling nonlinearity, if you will. Then each inside node, I reapply the operator u. So it's going to compute the average, and this is what I'm going to output, the average. And the next inside node of the next layer, which is the wavelet transform of these wavelet coefficient, modulus, second layer. To each node of the second layer, I apply the operator u again. It computes the average, that's a scattering transform through this path, lambda 1, lambda 2, output, and the third layer with the convolution with wavelets. And then you iterate. So you just have one operator u, which is contractive, and you just iterate on it. OK, what is the scattering transform, as I said? The scattering transform is the output. Let me come back to the previous slide. It's the convolution with wavelet and then averaging for any sequence. So in my network, that's the output in black. That's what I'm going to output. OK? Now, if you think, for example, what people use in audio, they just use traditionally these kind of output. They filter, average. These are what called MFCC coefficient or SIFT coefficient, are very close to that. Here, I'm going to show why the second layer is very important, and so on when we go down. How does it look compared to a neural net? Convolution, pooling nonlinearity, and averaging, which is a kind of pooling. The difference with standard neural net is that the output is not going to be at the end. The output is going to be at each layer. Some coefficient will go through one nonlinearity, some through two nonlinearities, some three nonlinearities, and so on. And what I will show, in fact, is that the energy of the network goes to 0 when the depths increase. So the outputs are at each layer. Second important thing, I don't learn the filters. The filters are given to me, they're wavelets. And they're wavelets because I'm dealing with translation. And I'll explain what you should do if you don't deal with translation. Okay, I'm going to explain intuitively now what is the information in this second layer. First layer is clear. It's basically wavelet coefficient. You extract information in different frequency band. What's happening in the second layer? And I'm going to give example on audio signal. An audio signal, a simple model, you have your vocal cords which are vibrating. That sends a series of impulses. Then it's filtered by the throat or by your musical instrument. H, that's the filter. And A is like the attack of the musical notes, succession. That's the amplitude modulation. So this is a very simple model of a musical signal or a speech signal. What's going to happen? First layer. The first layer is just taking your signal, convolution with the wavelet, averaging. Can easily show that it's going basically to extract the formant, the Fourier transform of H. That's what is characterizing the throat. That's what's characterizing the global structure of the sound. If you look at the second layer, convolution with the second wavelet averaging, what I'm going to show is that it then extracts the Fourier transform in some sense at different frequency of the modulation. So basically, I'm going to separate the H from the A. That's what's happening. I'm going to show you example. Okay, so this is a spectrogram with 3 sounds. That's wavelet transform. So I show in time, and the frequency is the index of the wavelet. So these are, you can think of it as wavelet coefficient. I'm going to play the sound. Okay, that's a tremolo, an attack. Okay? Now, this is the wavelet coefficient averaged. Now, because you average, you completely lose anymore the tremolo structure. You can't even differentiate these sounds anymore. Okay? Now, I'm going to look at lambda 1 here, at this frequency, and I'm going to compute, so this is the wavelet coefficient at lambda 1, convolution with the second wavelet lambda 2 averaging, and that's all the second wavelets. So I have a new image. Now let's look at this new image. Here there was very smooth attack. That's why the spectrum of the attack of A is very low frequency. You have a sharp attack, you see suddenly a lot of energy at higher frequencies. Tremolo, boom, suddenly you see appearing this sine wave. All the inner structure appear in the second layer of the network. Let's take another example, a vibrato. So the difference with the vibrato is that your vocal cord, instead of going at a like regular Dirac like that, they begin to oscillate. So they oscillate at a given frequency, and that's going to give the vibrato texture. So now you have a frequency which is the vibrato frequency of your voice. First order, I'll show, will basically give the harmonics of the sound. The vibrato information is not there. Second order, we'll see the vibrato through a series of harmonics. Let me show. That's 3 sounds. The musical note with the vibrato, you see the oscillation, and that's a tremolo, modulation of amplitude. Tremolo. They look exactly the same output of the first layer. So you can't distinguish these sounds from the first layer of your network. Second layer, you see what's happening. The tremolo produced, that's the frequency of the tremolo. But these two are different, and you see appearing because there is a whole series of harmonic which is struck, which is specific of the vibrato. So you see suddenly appearing in your second layer the information which differentiate these sounds. Let me give you another intuition of what's happening in the second layers of these networks. Suppose you have a simple signal, which is a sum of sine wave. So in the Fourier domain, it's a sum of spike at different frequency, omega n. Now you compute the wavelet transform. So the wavelet transform is basically going to isolate a frequency band for each of the wavelets. Okay? So the wavelet transform in the Fourier domain, it's a product of that with that. It's going to isolate these peaks. But what you do is you compute the modulus squared. So the modulus squared, if you compute it, you are basically going to get an energy, which is the squared term, and then the cross term, which is going to be the product of this sine wave, is going to give you cosine, which modulate with the differences of frequency. It's interferences that you're going to get. If you look at the Fourier transform of that, what do you get? You get an energy at the zero frequency, and you get an energy at frequencies which are not the frequency of the signal, but the differences of frequency. Difference between omega m and omega m prime. Think of a musical chord. If you hear a major chord, let's say an A major, unless you have a perfect pitch, which is generally not the case of most of us, you won't know whether it's an A, a B, or a C, Do majeur, Mi majeur. You just know it's a major chord. And you'll know the octave. Why? What do we hear? We don't hear frequencies. We hear frequency interval. What is a major chord? It's a minor third, major third, and perfect fifth, the differences of frequencies. That's what you hear. You hear frequency intervals. And that's exactly what's going to happen in this second layer. That's the Fourier transform. If you compute the second layer, that means you spread this with your second wavelet transform. You are going to isolate these frequencies, but these frequencies are really frequency intervals. So what are you measuring within your network? You are measuring interferences. Interferences between frequencies, and then third layer, interferences of interferences, and so on. That's another way to understand what's happening because of these modulus nonlinearity. Let me show you an example. That's a chord. That's the arpeggio of the chord. Same spectral content, but these are spread in time. Now, if you look here, because again, you are time invariant, you can't distinguish that from that. You've averaged. They look very much alike. If you had averaged more, they would look exactly the same. Second order, they occur at the same time. Because they occur at the same time, they produce interferences that you will see here and that don't exist here. These are called shadow frequencies that in fact we hear. And you see them appearing with the second layers. So you see that this information you are getting at the second layer is very crucial for understanding these signals. Let me show you two noise textures. Paper they have exactly the same power spectrum. In other words, if you sum the energy here and here, you get the same value. First layer will give you the same response because the first layer is basically giving you a spectrum information within a frequency band. Second layer, you distinguish them because there's structure here that is not here, and they appear in this second layer. Okay, images. These two images are completely different, obviously. That's their Fourier transform. They are different, okay? But you see, if they look a little bit alike, but they are different. If you make a wavelet transform, what is the wavelet transform doing? It's putting everything within pretty large frequency bands. So it's averaging that. Because you are averaging that, this and this is absolutely identical. Basically, that's what you would get with a sift vector that you would have computed not on a small window, but a huge window of the size of the image. Basically, the wavelet transform has very low frequency resolution. It can't distinguish these two images if you average completely. Second order, they are very different. Why are they very different? Because the interferences of this image and this image are totally different. Now, let's take these two textures. These textures are absolutely identical from the Fourier transform point of view. They have same second order moment. You take the modulus of the Fourier transform, they have exactly the same behavior. If you compute the first order coefficients, the output of your first network, identical because basically the Fourier transform is identical. Second order, they are totally different because the interference structures are completely different. So that's now to give you an idea why you do indeed have a lot of information within these second order layers. Okay, now I'm going to go back to the math and show you that we can understand very precisely what's happening within these networks. The reason why we can understand precisely what's happening is that, in fact, they are very simple if they are built that way. They are just built with a single operator U, which is a contracting operator. And as I explained, we just iterate over U. Apply U for each node, apply U, and output all the averages. Okay? We are iterating on an operator which is contracting. Again, what does contracting mean for an operator? That means that if I apply my operator on a signal U, X, and Y, this is going to be smaller than the distance between X and Y. Now, you have that, but at the same time, U preserves the norm. If you had a linear operator, this would imply equality, but it's nonlinear, so you can have the two. Okay. You are contracting, reapplying. If you cascade contracting operators, you get something which is contractive. So to understand the properties, so that's the transform, okay? For any pass P, I get this signal. And what is, so that's my phi, okay? That's my representation. Now, the norm of this is just the sum of the norm of all signals output by my network. So I sum over all the output node the norm of the resulting signal. That's the norm of my signal. Okay, first property. It's going to be a stable transform in the sense that the distance within the scattering domain is always smaller than the distance between X and Y. So if you have a small error, it's not going to blow out. Second, and that's obvious because you just built it by applying a contractive operator. What is much less obvious is that you preserve the whole energy. You haven't lost any energy because each time you've gathered the lost information. And that's going to be very important. Third property, which was what we wanted to begin with, this is stable to deformation. If my signal is deformed, the distance is not going to be 0, but it's going to be of the size of the deformation. Basically, the way to see this property is that you've linearized almost the small deformations. So in the scattering domain, a deformation is going to appear almost like a linear transform. That's going to be very useful because we'll be able to do linear classification despite the fact that the deformations are very nonlinear. Third property, what if phi, the window, gets bigger, bigger, and bigger? Then you should get something which is completely translation invariant. That's the case, and the scattering transform is going to converge. It's going to converge to something that it's a little bit like the Fourier transform. You know, the Fourier series converges to the Fourier transform. In the same way, this thing is going to converge to something which doesn't depend upon time anymore because you've averaged completely. And this object is going to look a little bit like a Fourier transform. Okay. I would like first to explain the energy conservation because that's one of the important things to understand the property of these networks. First thing, I said that the wavelet transform was a unitary operator. So the norm of the wavelet transform is equal to the norm of the signal. I showed that when I introduced the wavelet transform. U is a wavelet transform with a modulus, but if you take a modulus, you don't change the norm because the norm anyway puts a modulus over that. So this is something obvious. The norm, if you, well, the norm is a signal, if you compute the norm of a signal, you integrate the modulus square. So if you replace x by its modulus, you don't change the norm. Okay, what does it mean? It means that take your signal x, if you apply u, you get these signals. The sum of the energy of this with plus all this will give you back the energy of x. That's the fact that the norm is preserved. Now, each of them, you transform it. So the sum of the energy of all this is the energy of that. But the sum of the energy of these was giving that. So now if you add the energy of the output plus the last layer, you get the energy of x. Now, the last layer, you transform it. So the sum of the energy of all the output plus the last layer gives you x. Now, what's happening is that when the depths increase, you can prove that the energy of the last layer is 0. What does that mean? That means all the energy of the signal gets out of the network at different layers. You haven't lost any energy. And why is that the case? Because, as I explained, and it was mentioned, when you take a modulus, you take an oscillatory signal and you compute the envelope, which is a lower frequency signal. And then you are going to compute a modulus again. So you're going to get something even lower frequency and even lower frequency. So basically, you have a propagation phenomena in your network, which takes your high frequencies and propagates it back to the low frequency. And at one point, it's going to be so low frequency that the low frequency filter is going to get the energy. So it's going to be output. So all the energy is going to get out. And that's how you are building an invariant out of the very high frequencies by progressively bringing it back to low frequency. And then you have an obvious invariant. So that implies that all the energy that gets out, so the invariant energy, the scattering energy, will give you the energy of the signal. The second very important thing is that out of all these paths, most of them gives you 0. Why? Because you see, in your network, the information is going to go to lower frequencies. Here, if you arrive here, no energy is going to go to higher frequencies because there's nothing. Everything goes to low frequencies. So what's happening is that there are very few paths that gives you non-zero coefficients. And you know which paths they are. And as a result, the number of operations to compute that is in n log n. What does that tell you? It tells you that the whole structure of the network, you know it in advance. You don't have to guess the number of nodes at each level and how these nodes should be related. You know everything. And you can compute fast the output of your network. So we are in a situation where we don't need to learn the architecture, we know it. And we don't need to learn the filters, we know them. Okay? And we can compute fast. Let me just, for the fun, show you what's happening when the windows increase. So this is a signal, a simple indicator function of 0, 1, let's say, of an interval. That's the Fourier transform. It's a sinc function. It oscillates. Sorry, that's the modulus of the Fourier transform. Now, what I'm going to do is I'm going to take each of the paths, and for any frequency omega, I'm going to associate a particular path that I'm going to call P of omega. I don't tell you how I do that, but I can do that. And then, once I have P of omega, I give you the value of the scattering transform for this path. And therefore, I'm going to get a curve. Look at this curve. It looks very close to the curve of the Fourier transform. In fact, you can show that the energy within each interval is exactly equal. Now, why is that better than the Fourier transform? Take a Gabor function, okay? That's the same Gabor function. It looks very much the same, but in fact, it was very slightly dilated. So that's the Fourier transform of the Gabor function. It's a Gaussian at a certain frequency. And that's the same dilated, so you see the frequency support has moved. So the distance, if you subtract these two things, you get a very big number because they don't have the same support. Now, that's the scattering transform. So here, I have aggregated all the output of my network to get a curve. I don't tell you how, but you can do it. That's the same curve corresponding to this signal. Look at these two. They are not the same, which is good because you've changed the signal. You don't want them to be the same. But the support hasn't moved. It's just the amplitude. So now, if you look at the distance divided by the size of the deformation, it's of the order of 1. You are stable to deformation. Here, it was the order of 10, and I could make it go to infinity. So the point is, you see it appear, you have something which is now fully stable to deformation. Okay, so is stability really useful? I'm going now to show that stability is very crucial for a large set of problems. However, invariance to translation is not going to solve the world problem. I want to insist on that, and I will further discuss these issues tomorrow. So I'm going to show how to apply the most naive classifier out of such a transform. So the spirit of all what we're doing here, and it's really the spirit of this kernel learning, is to say you have a nonlinear representation, like a deep network, and then you apply a linear classifier. It can be an SVM. I'm going to do something even simpler. I'm going to use a PCA. So I begin initially to illustrate the thing with two classes. So that's in red the point of my class 1, and in blue the point of my class 2. And in the original space they are spread everywhere. It's a mess because the formation doesn't maintain things close, or you may have all kind of variability. Okay, what's the idea? The dream is that you apply your kernel, your scattering transform, and by miracle, everything now gets aggregated in a nice linear space, whereas the blue point gets aggregated in a nice linear space, and you are going to use that for the classification. So how are you going to learn the linear space? Well, you're going to do a PCA. What you do is you get, so now I'm doing supervised classification. I know the label of each point. So I take the points of the class 1, I transform it, I get new points. Now I'm going to compute the covariance matrix of these points. I'm going to diagonalize the covariance matrix, extract the eigenvectors, that's the PCA, and the largest eigenvectors will define the linear space which best approximates the point of the class 1. Now class 2, I'm going to get the center, the average. I'm going to compute the covariance matrix, diagonalize it, get the largest eigenvector. It will define the linear space that best approximate these two. So I have two affine space. The first affine space that goes through the centroid with the first eigenvectors, and the second one like that. And now I take a new signal x here. I map the signal x with my transform, and then I try to find whether this is closer to the space of the class 1 or closer to the space of the class 2. I just make the distance, and I select the class which gives me the smallest distance. Okay? This is the simplest classifier you could think of. So to do that again, what you need is for each class compute the expected value, the average of all the test samples of the transform with the scattering transform. You need to compute the covariance, you need to diagonalize the covariance, and extract the principal vectors. Now, you have to fix the dimension of the approximation space, D. This, we are going to do it with cross-validation. If the dimension is too big, then basically your space are not going to discriminate anything. If it's too small, it's not going to have enough regularization power, so we are going to choose the best D out of the test sample. And we're going to apply that to MNIST, okay? So you have a lot of deformations. This is the most standard classification problem. So what does it mean on MNIST? It means the following. You take your signal, which is there. I'm not going here to need to have something fully invariant to translation, because the digits move but don't move so much. So the size of the invariant here is going to be of the order of 8 pixels. The scale of the invariant is learned automatically by the algorithm by doing a cross-validation. So that means that I'm going to make an invariant over windows of that size, okay? So for each window, I have the scattering coefficient at the order 1 and the scattering coefficient of the order 2 that corresponds to that kind of regions. And then I have a window here. These are the coefficients. And a window here that are the coefficients. So basically you have 16 windows, order 1 coefficient, order 2 coefficients. So now you have a vector of coefficients. Now I take this vector, send it compute the average over the class on the test sample, compute the covariance matrix, get the eigenvectors, and so on. This algorithm is very fast. There is no unsupervised learning. You have an n log n algorithm to compute the scattering transform with just a cascade of convolution. Then you have a PCA to compute. So basically, you can run it on a laptop like that. Now, the surprising thing is that you get the state of the art over all published publications over MNIST. The state of the art was in fact obtained by Yann Lequin with convolution net. So in some sense, this is a convolution net. You get the state of the art at all training size, whether it's 300, so very few samples, up to 60,000. Okay? And you go back to about 0.4%. Okay, so what are you doing when you are doing that? You are doing the following thing. What's happening is that in your original domain, what was difficult for classifying digits, by the way, if you just do a PCA on the original digit, you get a very bad classification rate. When you go from a digit like that to a digit like that, the points in your original domain is going to move widely. In the scattering domain, because you are stable, the points are going to move by the amount of deformation and linearly. So if you look at different deformations, you are going to get a set of points, and because they move linearly, you'll be able to find a linear space. And what's the dimension of the linear space here? It's going to be basically the number of free parameters that defines these deformations. Now, if you take a 2 is going to be sent normally in different places. But also, a 2 has different type of deformation. They're not the same than here. So if you look at all the deformations of the 2, you're going to get a linear space, not only which is centered at the same point, but which doesn't have at all the same directions. And that's why then when you take your thing, a simple distance to these linear spaces will be discriminative. But these linear spaces are very informative. They characterize not only, in some sense, the template, but also all the possible deformations that were learned from the test element. Okay? So that's why it's very important to stabilize, because the final classifiers are linear. Whether you do it with SVM, it's the same. SVM was getting basically the same rate, sometimes a little bit better, but it just requires more computations. And also the interpretation is simpler when you do it with a PCA. So I prefer to show it with a PCA. But the final layer of the supervised classifier is a linear operator. So you need to make sure that your nonlinearity that you've applied before is going to transform the variability of the signal in such a way that a linear operator can capture it. And that's what it means, stability. Stability means that this nonlinear deformation, when in the case of translation it was deformation, is going to be translated into a simple linear movement in your space that can be captured by a linear operator. So that's why in all these things, yes, the issue of stability is coming at the core. I realize now that I went a little bit faster in the second part. What I'm going to show afterwards in the second part is several points which are complementary to that. The first point is the issue of inverse. One of the questions is how much information do we lose? Yes? Okay, I'm going to, yes, here it's very similar, and in fact it's a very naive manifold. It's a piecewise linear manifold, so it's a very naive way. If you want to compare the overall approach to manifold, the big difference is the following. I don't consider to begin with that my data lies in a manifold. I try to find a representation which is going to map this data to a linear manifold. So when doing that, I'm killing some of the variability of the data, which originally was not at all in a linear manifold. So I think, and that's something which is important in all these networks, the assumptions to begin with is not that the data is on a manifold, but is to find a way to map it to a regular manifold, and then you can apply your manifold tool to do the classification. Yes?
Optimal dimension is different for different classes, right?
No, in this case, we impose to have the same. You are right that it could be different. And we began by allowing to have something different and then having a penalization technique out of the dimension. And then we realized that setting the same was giving a result that was as good. But a priori, you are absolutely right. There are classes where the dimension could be different. And then there are, as I said, ways to handle the fact that your dimension space could be different. Yes, it's in no. Okay, concerning this issue of inverse, it's a very tricky issue because we are not so much interested in reconstructing, but there is constantly this question, are we losing information or not? And are we losing relevant information? So that will be a very important element. A second element I want to stress is the following. In all these classification problems, one of the very difficult elements is the fact that we have very few samples to learn from. The number of tests, MNIST is not a realistic problem. You never have in life 60,000 examples to learn from. Imagine that you need 60,000 examples to know what a lion is. If you need to meet him 60,000 times in the jungle, you have very little chances to have any children. Okay? So that's, in Darwinian terms, means that your recognition system is not quite optimal. So the whole issue of learning is about learning out of 5, 6, 10 examples. Okay? What does that mean? That means that you need to learn statistics out of very few samples. Now, when you have very few examples, you cannot dream to learn the whole probability distribution of your signal space, compute log likelihood, which are realistic, because you don't know this distribution. You can't even compute second-order moments or third-order moments because you have very few samples. If you look at the variance of second-order moments, it's very large. That's the whole problem, is how to compute descriptors that you can estimate with very little variance. And to do that, you want to use compressive operator. That's one of the reasons why compressive operators are very useful, because if you compress, that means that you always reduce the variability. That means that you can estimate averages with fewer examples. You're not blowing out variability. When you take a square, you blow out the variability. So to compute an expected value, second order moment, it requires a lot of samples. Third order, fourth order, it's even worse. So that's another very difficult aspect of classifications. Okay, so I'll break here and we'll resume tomorrow. Thanks very much.